Jakob, in his research, was interested not only in quantum gases. I mean, he did the work on algebraic quantum field theory. And one of the things which is important in algebraic quantum field theory is the energy momentum picture. Is in fact, the spectral condition, and so maybe he will like the fact that here there is also an energy momentum picture, which actually already appeared yesterday in the talk of Valentin, and I'm really happy. I mean, this is one of the most striking pictures in the whole physics, in my opinion. So I will speak about research about work which I did with Lorenzo Pettinari, who is here. He's not invited, but he's here. And also this is a continuation of my work with Marcin Napiórkowski and Ben Lee. Marcin has been invited. This is the dispersion relation of quasiparticles in helium-4. This is according to a relatively recent experimental paper, so from 2021. The pictures that Valentin showed were more historical, and here it is written that error bars are not visible at this scale in most of the range. So this is really very sharp, although not infinitely sharp. In fact, even theoretically, this is broadened, but you cannot see this apparently in this picture. Maybe in this region. In fact, each region has a name. This is called these are called phonons. These are called maxons, rotons, and Pitaevsky plateau. Now, I will speak about, this is motivated by helium, but this is a mathematical result. We consider a homogeneous Bose gas with a weak two-body potential and a C number density of the condensate and low temperature. Temperature can be also 0. In a large periodic box of size L. As is well known, and I think this appeared in some talks, if you compute the quasi-particle dispersion relation following Bogoliubov's recipe, you get this formula, which essentially reproduces this picture, at least qualitatively, not really quantitatively. So in particular, for low momenta, you have the phononic dispersion relation. This dispersion relation is expected to be broadened by the interaction with higher order terms in the Hamiltonian. And this broadening can be described by the imaginary part of the dispersion relation computed in perturbation theory, at least in principle. And so here I will use the perturbation expansion in the coupling constant to the potential. I know that this is not the most physical approach, but the title of the workshop is Mathematical Perspective. So yeah. Now, for positive temperatures, it is convenient to use the Liouvillean instead of the Hamiltonian, which involves doubling of the Hilbert space. If you have, so this is the doubling of the Fock space. So one has two kinds of particles, and I will call them left particles and right particles. Maybe there is a better name, but and so we would like to compute the imaginary part. We will use the Fermi Golde Rule. So this will be the lowest non-trivial term, and we keeping the condensate density fixed and temperature fixed, and taking thermodynamic limit. And so the imaginary part turns out to be the sum of two terms. One is called the Beliaev damping, the other Landau damping. So this Beliaev damping persists down to the zero temperature, and it is caused by left quasiparticle decaying into two left quasiparticles, and the Landau damping is absent at zero temperature. It is caused by a left quasiparticle decaying into one left and one right. Now, to describe the formulas and to understand the behavior, it is good to note that you have two natural parameters. One is the momentum, and it is to get a dimensionless quantity, it is good to divide it by the square root of the condensate. And one has also the temperature, and so this is the dimensionless version of the temperature. And we will also use the ratio of these two. So this is the Beliaev damping. There are two regimes depending on, so everything is for small momenta, but the ratio of the momentum and the temperature is either going to zero. So here, this is the ratio of temperature over momentum. Either goes to zero or to infinity, and there are two different asymptotics. And a similar statement about the Landau damping, where also the temperature is supposed to be small. Now, of course, there is a long history about this. So the Beliaev damping for this rate, for the temperature over momentum going to zero, was first derived in a remarkable paper by Beliaev, around the time when I was born, when I was being born. So that's conversely, in the other limit of the ratio of temperature and momentum, we get the low temperature of the Landau damping, and apparently it was computed first in a paper by Hohenberg-Martin slightly later. Now, and so, well, our work is, I mean, we try to put these computations in an orderly fashion. I mean, one should be somewhat modest. Well, we're trying to understand this in a systematic way. That's our contribution, one can say. And let me try to. And in fact, there are several ways how you can present this, and I will present two rather distinct derivations. But both of them start from the Hamiltonian with a C-number condensate. So this is not the Hamiltonian which was used so far in this conference, because the zeroth mode has been turned into a C number. But this has a very long tradition, and it it has some heuristic justification, and so it is in a periodic box, and of course written in second quantized form, and so you take the usual n-body Schrödinger, many-body Schrödinger operator, and you replace the zeroth mode by the square root of nu, and we also put the coupling constant to be kappa. There is then one can dropping a constant. One can divide the Hamiltonian into three parts. There is a quadratic part, a third order part, and a fourth order part. So the quadratic part does not depend on the coupling constant at all. It depends on the condensate, of course. The third order part has the square root of the coupling constant in front of it. And the fourth order has the coupling constant to the first power. Yes? Okay, I probably didn't. So that okay. This is you replace okay. Suppose there is no kappa. You replace the zeroth mode with the square root of nu. Then you get this with kappa equal to 1. Do you agree? Now, I think you should. Okay, you should probably replace the zeroth mode by nu times the square root of kappa, or divided by. Now I cannot think that fast, but this is what you get. And, it is a translation invariant Hamiltonian, and as everybody does, you can diagonalize the quadratic part using the Bogoliubov rotation, which amounts to replacing the usual creation operators by combinations of new creation operators with appropriate coefficients, and what you get is the well-known expression, and you get the dispersion relation, which I already mentioned. The intermodynamic limit. So the dispersion relation does not depend on the size of the box. It just samples this function. Formally, if you formally the Bogoliubov Hamiltonian has a limit, thermodynamic limit, and its spectrum has a singular shell along the dispersion relation. Now, the interaction with the third, but the full Hamiltonian contains two additional terms, so they should broaden this dispersion relation. Now, how to describe this mathematically is actually not so obvious, and I will try to present two approaches. One is inspired by operator algebras, by the theory of C-star and W-star algebras. It is, and also by ideas of Jakšić-Pillay. It is actually not, well, you will see. I mean, and the second is the method, one can call it the method of green functions. It uses two-point correlation functions. So it is more inspired by the usual formalism of quantum field theory. And I can imagine that there are other approaches. Well, okay, so suppose we have a quantum system described by Hamiltonian and the Hilbert space, and yeah, the evolution will be denoted in the usual way. Now, the observables are described by are self-adjoint elements of the algebra of operators. Now, I insist to use the so-called standard representation of this operator algebra. The standard, the standard representation in this case means that we act by multiplication from the left on Hilbert-Schmidt operators. So the product is the trace of, I mean, the usual Hilbert-Schmidt product. B for bounded to for the second. I mean, the Hilbert-Schmidt is like L2, like the L2 of measure space. So you have two commuting representations: the left one, multiplication from the left, and the right one, multiplication from the right by the Hermitian conjugate. The dynamics. There is a natural way to generate dynamics. So this is called the Liouvillean. The Liouvillean is the commutator with the Hamiltonian, and it is a self-adjoint operator in the standard representation. Every normal state on this algebra has its standard vector representative, which is just you take the density matrix, you take the square root of this density matrix, and then the state becomes is purified, is a vector space, a vector state. In particular, the KMS state is given here. Now, I mean, honestly, you may say that this is an overkill to use such big words, and I know that in the room there are how to say enemies of C-star approach, but I mean there are also some. No, okay. Yeah, but so in fact, you don't need this, and all these von Neumann algebras are of type 1, which are trivial from the point of view of operator algebra people. So now, actually, the standard representation, the naive standard representation, is not very convenient. But it can be improved by passing to the so-called Araki-Woods representation, which use the Araki-Woods representation adapted to the Bogoliubov-Liouvillean. So you have the Hamiltonian is the sum of the Bogoliubov-Hamiltonian plus the perturbations. So now the Liouvillean, the full Liouvillean, is the sum of the Bogoliubov-Liouvillean plus higher order terms. And in this representation, the KMS standard vector is mapped to the vacuum, to the Fock vacuum. Well, this is very convenient. And the creation and annihilation operators are then represented in this form. So you have the left creation and annihilation operators, and the right ones. And here, so this is an old. I mean, this goes back to maybe probably late 60s or early 70s. The free Liouvillean and the standard momentum. So every operator has its standard version. Can be written in the second quantized form. These are quadratic operators. And they have a positive and negative part. And now in thermodynamic limit, the joint spectrum of the Bogoliubov-Liouvillean and standard momentum is the whole space. It's called space-time, actually. So 1 for time and 3 for space. And it has a bound state corresponding to the KMS state, I mean the vacuum. And now, in thermodynamic, you can take the thermodynamic limit, and the thermodynamic limit has two branches. It has an upper branch and it has a lower branch. You can, if you look at standard textbooks on many-body quantum physics, then you can see actually such pictures. So now you have kind of two kinds of quasiparticles. In the Araki-Woods representation, as I said, the KMS vector is the vacuum. And now, by general principles, if you perturb the system, then the KMS the KMS there is a good perturbation expansion for the KMS vector, and its energy will stay zero. It's in this standard picture. So in particular, this will be important. If you do the perturbation theory, then you will get 0, 0, 0. All the terms will be 0. Now, suppose we are interested in a phonon. There is a creation operator of one phonon. So, but to get a standard vector representative of a phonon, you have to create one left phonon and one right phonon, and you have to act. So this is kind of a. Physically it is one quasi-particle, but you need to act with two creators. And it is an eigenstate with eigenvalue 0, 0 of the Liouvillean and the standard momentum. After switching the interaction, it will yield perturbed eigenstates of the Liouvillean. But however, these eigenstates will not survive thermodynamic limit. If you compute the shift of eigenvalues in thermodynamic limit, it will produce an imaginary part, which you can compute. So this is the formula. This is the Fermi Golde Rule with the third order perturbation, and this is sometimes called Feynman-Hellman term for the fourth order. They are the same order in kappa. But actually, since we are interested in the imaginary part, only the Fermi Golde Rule will play a role. But so this is the naive formula. But if you do this, you don't get anything interesting, because you have to subtract something which is extensive in volume, but which is 0 when epsilon goes to 0, by the argument, by these properties of the KMS states, which I mentioned. So this is what I explained. Okay, this was the first method, and from that you get the formulas. Now there is a second method which is now this is for the lovers of quantum field theory. I mean the previous was for the lovers of operator algebras. Two-point green function. I mean the two-point time-ordered green function is if you have two observables. This is the definition. This is the expectation value. This I is for convenience, and you go to the energy representation. So E is a real, and there should be minus I0 here. Yeah, so there is a misprint, but yeah. Yeah, so minus I0. Now this here. Now following Beliaev, we choose the creation and annihilation operators for these observables. So of course we have four combinations. So we get a 2x2 matrix of green functions, but actually it is more convenient to use these Bogoliubov rotated creation and annihilation operators, and this is what we will use. And so we have a matrix of 2-point functions. Now for the pure Bogoliubov Hamiltonian, one can compute this exactly. And one gets two branches. I mean, one gets two branches of delta functions. One coming from the left quasiparticles, the other from the right quasiparticles. Now, when we compute the dispersion relation by perturbation theory, we expect to get some negative imaginary part. Well, negative, so here there is minus I0, so it works well. This will be pushed to the lower half plane. So now if E is real, then this will look something like that, and this will produce a bump instead of a singular shell. So these singularities will be now damped, and the damping will be proportional to the imaginary part. And now in the lowest order of perturbation theory, I mean, we compute this shift, and the computation is very similar. You have Feynman-Hellman for the fourth order perturbation, Fermi Golde Rule for the third order. And then we have to subtract the extensive quantity, which which goes to zero anyway. But here it has to be, and we get well, actually. The real part, in the previous computation, the real part was zero by some general symmetry, so there was no issue. And now here, the real part is divergent, which well, this is a very primitive calculation, and if you improve on it, as Beliaev did in his old paper, then you get actually a finite real shift of the dispersion relation. But anyway, for the imaginary part, we get a finite quantity, which agrees with the previous computation. So agrees up to the factor 2, which is also well understood because you Now we take only one creation operator instead of two creation operators, and this accounts for. How much time do I have? 10 minutes. Oh. Yes.
You get a different result in the two approaches.
Yes.
How's
yes.
it possible? I mean, I thought that these are just two ways of
No, no. These are. It's not obvious that. No. Okay, maybe I can use the blackboard. So the unperturbed picture is this. So this is 0, and now the first picture concerns perturbation of a vector. So this is really a perturbation theory in a Hilbert space. So I mean this is for the Bogoliubov Liouvillean, this is a multiply degenerate eigenvalue. It contains the KMS state, which coincides with the vacuum, but it coincides. It has also this maybe. The momentum of this is 0. The energy of this is 0. So it's a very degenerate, and we do perturbation for some vectors from here. So if we do this for the vacuum, then we get the KMS state, and it will still be 0, 0. But if we take this standard vector representative of a one mode, then we will get something, and in finite volume we will get some screwy, I don't know what. But in thermodynamic limit, this converges to a nice formula with a negative imaginary part. So this was the first approach, and the second approach, you take a vector, something which sits here. So a priori it's a different. Okay. Any other question? Yeah. So just to show the formulas. So these are again these hyperbolic cosine and sine for the Bogoliubov transformation. I mean, well, this is something which can be called the amplitude of a 3 quasi-particle vertex. And so this is the formula for the Beliaev damping, and this is for the Landau damping. So this is in the weak coupling limit. So if you there's some ladder diagrams as well. So if you want to, which is physically a good thing to do, and then essentially the strength of the potential first of all, V hat will be a flat, will not depend on the momentum, and you should replace it anyway by the scattering length, essentially. I mean, more or less, and then you get the formulas which were written in the old papers from the 50s and the 70s. But sort of, we thought that this weak, also already with Marcin and Ben, we thought that this weak coupling limit is somehow cleaner mathematically yeah. And I think I am finished. And happy birthday. Yeah.